So far, I've talked about the CPLD core and FPGA core like everyone knows exactly what I'm talking about. This is something I want to sort out so that what happens in the HDL code makes some sense. Before I can talk about the two cores, I need to explain what I'm replacing with them. I've mentioned it previously, the Motorola 6809 reference design, or just the reference design. It sounds like something mythical, a terminology we still hear, but to be fair, it is just a document that illustrates how some new hardware works. Whether it is an 8-bit CPU and supporting chips or the latest consumer-grade GPU. In this case, it is the combination of the 6809E CPU, 6883 SAM and 6847 VDG. This trio of chips mixed with a couple of the fairly versatile 6821 PIAs for external I/O duty, plus supporting logic, ROM and some DRAM, is the basis of a fairly minimal 8-bit computer. Pretty much an off-the-shelf design that doesn't need much to become a practical consumer package. It turns out that Tandy, and later Dragon Data, took the design fairly literally, and both the Color Computer version 1 and version 2 and Dragon 32 and 64 are basically just the reference design with a few bits of decoration. The 6809E is obviously the core of the system, but without the SAM and VDG it can't do much unless you add a substantial collection of additional logic. The SAM takes the CPU address bus and turns it into a set of 8 device select lines, as well as handling the cumbersome job of DRAM refresh cycles. The VDG is designed to be a standalone display generator, but coupled with the SAM, it can offload its very limited address register and rely on the SAM to manage such things and get its own dedicated slice of the clock cycle to avoid horrible contention problems. Sounds great, but unfortunately the VDG isn't just limited by the addressing, it is also a product of the very early 8-bit home computer era, when the Commodore PET and Acorn Atom was state-of-the-art. The Atom did use the 6847 for its display. Compared to the original TRS-80 and the likes of the ZX80 and 81, it is favourably specified, but we know just how fast things were moving in those early years. For the Coco, it was a colourful revolution. Not so much compared to the VIC-20, but by the time the Dragon hit the shelves, it was old hat. Don't get me wrong, the Dragon was my first computer, and I loved it, forgiving it all of its uppercase-only sins and awkward 4-colour bitmap palette. I've had 40 years to ponder this, and I want to fix it with some upgrades. That means taking the 6847 and putting it where it belongs. There is only half the problem though. The other half is that by the time Dragon Data had a 64K version of the Dragon, everybody else was on 128K or more. The SAM puts a stop on more memory though. That isn't to say it can't be done, but you really need a later revision of that chip to make it work. So what if I smushed the SAM and VDG into a single device? The equivalent of the specialised ULA chips that other manufacturers were using, and even Tandy resorted to with the Coco 3. Actually, I can cheat a bit there and reuse the Coco 3 specifications, at least in part. The number one goal is compatibility. The baseline device has to respect the SAM and VDG behaviours as far as possible so that existing hardware and software continues to function. Once that is done, the next goal is more memory. Kieran Anscombe has pretty much solved this for me with his SAM X8 upgrade, which gives you 512K of RAM by replacing the SAM with a CPLD implementation plus upgrades. Goal 3 is upgraded display capabilities, using the Coco 3 Gimme chip as a guiding light. Upgrade the colours and resolutions generated to at least put a stop to the smirks from the back of the class about the buff colour set. The SAM replacement is largely something I can adopt, proven to work and open source. The VDG is a different beast. HDL implementations already exist thanks to the MISTER project, but they only partially meet the hardware requirements. Doing this in real hardware means getting the video out into the real world through a low-tech composite signal. At face value, this isn't so bad, except that the 6847 outputs a raw monochrome NTSC video frame plus colour channels that approximate together to a YPRPB signal. Existing projects output a digital RGB signal instead, which is something of a different beast. I could go to the trouble of generating YPRPB, which would allow me to retain all of the existing display circuitry, but I think that would be missing the point of being able to generate a superior display. Not to mention, if I am upgrading the colour palette, the programmer is going to want to use RGB to specify palette, not the raw colour space. The answer is to make sure I generate composite and ignore the rest of the display hardware. This has the added benefit of being able to generate PAL and NTSC composite from a single device and avoid the extraneous circuitry needed there too. Fun fact, 50% of the logic on the Dragon computer circuit board is just to convert NTSC into PAL. It just so happens that this particular problem is not new. It's been around for almost as long as the home computer and digital TV controls, and you can still buy new ICs for handling the conversion from RGB to TV signal. The weapon of choice here is the analog device's AD724 or AD725, with the caveat that they are getting a bit expensive. More on that in a mo. This little chip turns RGB and the sync signals into fully fledged composite with the added bonus of S-Video, separate Luma and Chroma signals, and can switch between PAL and NTSC formats. It needs an analog input though for the 3 colour channels, and they have to be conditioned to suit the expected voltages used in the video transmission. I originally used a simple R2R resistor ladder for digital to analog conversion, but this never worked quite as well as I'd hoped. Thankfully, you can buy another chip that solves the problem. This time, it is the Texas Instruments THS8136i PHP. A dedicated 3-channel video DAC designed specifically to convert 30-bit RGB into ready-conditioned analog RGB. As it happens, I only need 12-bit RGB, but tying the lower 6 bits of each channel down is not an issue. At this point, I want to cover the elephant in the room that is the pricey AD724. One of the things that has happened in the last 5 years is the growing prevalence of upscalers and converters from RGB to HDMI, and the diminishing availability of TVs that handle composite or S-Video. Outputting HDMI is the most convenient standard now, and you can buy ready-made devices that do this for you. Typically, you would need something that converts the YPRPB format used internally in many computers, or if you're lucky enough to have a computer that uses RGB, take a bit of a shortcut in that respect. Even just outputting analog RGB is an improvement, so why do we need the composite video signal? For purists, this is almost essential. HDMI is just too sharp and crisp. If you want an old CRT, then HDMI isn't even an option, unless you are incredibly lucky. My choice here is to give you the option. RGB is the output as standard, and you can add a converter to composite if you want it. What about the core then? With the supporting video hardware described, I can finally talk about the real work in this project. Very briefly then, in terms of history, I started out with a very modest CPLD to reproduce the VDG. It turns out you don't need all that much. It is, after all, a very simple display generator. You have to use a ROM to hold the character set, but it fits in just 128 macrocells. The problem there is that the symbiotic relationship between the VDG and SAM means a distinct lack of control and a timing headache that can ruin your day. Or at least mine. If I combine the two, I can get everything in a slightly less modest CPLD, removing any timing issues, streamlining the implementation and allowing for some extra features. Or it would if that not so modest CPLD was enough. It turns out that the enriched palette controls use way more resource than I'd anticipated, and I need even more resources. So that has pushed me to using one of the largest CPLDs that you can still buy new, and it turns out, thanks to price fluctuations, that the bigger CPLD isn't actually much more, and very occasionally is actually less. The device of choice for now is the Intel EPM 1270. About 10 times the resources I originally started working with, but very importantly, still using a package that is relatively easy to work with. The alternative is to switch to using a modern ball grid array package, and that brings a whole world of pain and cost in comparison. The EPM 1270 is not a powerhouse, but it is current. A generation on from the first chip and better in every way except one. It doesn't handle 5-volt logic. That means that every input and output interfacing with the host computer needs level shifting hardware to convert between 3.3 volt logic and 5 volt logic. Fortunately, there are some very good devices for that. My particular favourite is the TXS-0104 and TXS-0108. These work on a push-pull basis for flow direction, so no need for direction control. It isn't magic, and there are considerations to be aware of, but for my purposes, it is a very simple solution. On the plus side, the video DAC operates on 3.3 volt logic for its input, so at least some of the signals are usable directly. The big issue is that I still need a ROM to hold the character set. I could abuse the CPLD and squeeze the default internal 6847 character set in, but given I'd like to have lowercase as an option and maybe even different size fonts, a dedicated device offers lots of benefits. A slightly smaller but still significant issue is the memory. I get the prototype versions of these boards ready assembled from the factory to remove my slightly inadequate soldering skills from the equation when testing. The headache is making sure the stock of SRAM chips is there, and this really is a headache. I've had to rework the design a few times just to meet this requirement. Every time I have a prototype built, it has been a different SRAM chip, or chips. This area of the board is deliberately left largely empty so that I can quickly rework things as needed. The rest of the components on the board are either decoupling capacitors, power management, or a timing signal. The CPLD and level shifters need a fair few capacitors between them, and I need to provide 3.3 volt and 1.1 volt voltage rails. The timing signal is actually the master clock for the whole computer, managing the CPU's clock, memory access, and the video pixel clock. The board itself is reasonably large, but there is a reason for this. It has to accommodate the FPGA version too, keeping all of the connection points to the host in the same place. One of those connections doesn't go to the host, but is rather important, the JTAG connection for programming. In a nutshell then, that is the physical hardware of the project. The differences between the CPLD and FPGA versions at this point are trivial, but I will go into those in a later video. Next time I will dig into the HDL code that defines how each part of the solution works. For now though, being a real YouTuber, please like and subscribe, but even more importantly, leave your thoughts and feedback.